So hello everyone. So we're going to start. So as the same as yesterday, if you have any questions, you can put into the chat, and you can also unmute yourself and just ask directly, since we don't have a large number of attendants here. Okay. So I will again just share my screen. So you should have received the package as sent through the email getting. And again, for the image for beginner 2, this is basically the slide we're going to use for today. So for today, it's mostly kind of a demo getting. As yesterday, we talked about that you can, if you have an image, like say a cell, like a simple one, you can manually draw them one by one, and then you can put them into what we call the ROI manager, because every single cell, once you draw them, you create a region of interest, the ROI of it. And you can save out the cell outline you draw into the ROI manager, and you can do the measurement on each single one of them. So today we're talking about, probably you are more interested if you can ask the program to do this automatically. That you have an image, each image has like 100 cells. You don't want to manually draw 100 cells. And more than that, you may actually have 20 images like this for one condition. For another condition, you have another 30 images. You definitely don't want to draw them one by one. Okay? And so the image analysis program can do it. The ImageJ can do it, but it's totally dependent on how good you can, what we'll say is a thresholding it, or the segmentation. Okay? And the thresholding is what we're going to talk today. And basically, this is, I would say, it's the centerpiece for all the digital imaging analysis. Once you begin to working on to analyze your images, you will realize everything depending on the thresholding, how good you can do. So basically what the thresholding do is, we will create a mask image, or what we call the binary image. So I will go to the image thresholding folder, and I will open this image. If you're trying this on your own computer, just make sure, do this first. You go to the edit, options, color. Make sure the foreground color is white, background color is black, selection is yellow. Click OK, and then go to process, binary options. Click this one, make sure this black background one is checked. Since today we're just working on the binary images, it's very important to make sure this black background, the background checkbox is checked. So let the program know we're working on the white object. Once it's set. So I would say this is, I will call actually a fake cell. It's not really a cell, okay? So my goal is to say, identify how many cells inside this field of view. And I want to calculate the size and the mean intensity. So as we did yesterday, we can kind of zoom in. And I can use those freehand. I can draw those cells. I will draw them. I press the T on my keyboard. I will add them to the ROI manager. And then I can begin to draw more cells. I can add them. Okay, add it. So I can say this will be the 3 cells I have. That's we already can do. We have those ROI manager. I can save it. So it can show us later how I select this cell. And I can also use the analyze, set the measurement. Let's say I want to measure for each cell, I want to measure the size. I want to measure the mean intensity and the total intensity. The integrate density actually means the total intensity. And then I can do the measurement here. It will give me the size of each cell, the mean intensity, and the total intensity. but this has quite some cells in it. I would say, by my understanding, when I look at this image, I would say it's kind of very simple for me to identify, to draw the cell. I don't need to know much about the cells. Now, for my instance, I can ask my daughter who is in the 4th grade to actually draw it. I will just tell her the white one is a cell. And then I think she can draw it. And he can draw it probably much better than I do it. Okay? So since I think it's not very difficult, so why not if we can ask the program to do it for us? But then the problem for the program to do it is it doesn't know which pixel belongs to the cell, which pixel belongs to the background. For us, when I zoom into it, let's say this is a cell. So when I identify the cell, I basically, the parameter I will use to identify the cell is the intensity value. I will say if the intensity is higher, which is white here, I will say that is the cell. If the intensity is low, like in this part, then I will say this is the background. So let's say if I draw a line, I use this line, I draw a line, and I can use the, I think this, the analyze plot profile. It actually plots the intensity throughout the distance I draw it here. So I will say I started from here. This is where this is low. And I go through, this is a cell. It goes up, it goes down, it goes to another cell, goes down. So when I look at this curve, I will say probably this part is, I will ask someone, if you do not speak, please turn off your, please turn off your microphone. So those parts are the cells, and those are probably the background. So I think maybe I can use this intensity as a kind of the parameter to set to tell us which pixels are the cell, which pixels are the background. Because the difficulty for the program to draw the outline is that it doesn't know what is the cell, what is the background. So we need to give the computer, the program, a very simple parameter to say what, when you count on one pixel, what makes this pixel be part of my cell, my signal, my object? What pixel belongs to actually to the background, which I don't care. Okay? Here I may say maybe the intensity can be a good one. Maybe I will say about 100. Everything down here is probably around here. This is the background. The intensity, most of them are actually below 100. And if it belongs to a cell, it should be above the 100. So I think this, maybe I can use one parameter. In this case, based on the intensity, I will call it the thresholding. So I will say for all the pixels here, we have a digital image, which is basically a 2D matrix. I have a 256 times 254, about this many pixels. Each pixel has a value. I would say for every single pixel, I check on the value. If that pixel value is below 100, I would say that pixel belongs to the background. I don't care. If that pixel intensity is higher or equal to 100, that is part of my cell. I actually want it. Ready? Then I want to check to say, will this work? Ready? So to check on this is what we'll do is the thresholding. As I said, I think the thresholding is the centerpiece for all the digital image analysis. So I will say, as long as you do the image analysis, you will always use this function. That will be the image adjust thresholding. Okay? This is use the intensity, pixel intensity value to divide all the pixels into two groups. I click on this. It gives me this. So what you can say is, if I look at the thresholding, I use this one, you check this one to the red. So now you can see two bars here. Y is for the upper threshold holding limit. This the upper one is for the lower threshold limit. You normally set the upper one to the maximum intensity available. This is 8-bit image, so the maximum intensity available is 255. So this is what I want to go through. So if I set this to 100, as we just did, now everything shows up red here. Is the pixel intensity is bigger or equal to 100? Every pixel shows its original grayscale has its intensity value lower than 100. So you can change this one to be a higher one. So now we're looking at pixel intensity has to be higher than 120. You can say it's the red part of the image getting smaller and smaller because we're asking the pixel intensity to be higher and higher. And if I move down, you can see the red area getting bigger and bigger. So our goal is try to set up the value, which this one apparently is not good, it's too high. This one will be too low. I will try to set up a value which I think is a good one. I think this represents what I actually humanly looking at this. I open here again, just we can say them one by one. So I play around this. I will say what value which give me the red region, which I think it best represents the cell here. Before I said probably 100 is good. Now I feel 100 may be a little bit too much. I want to go up a little bit. I will say 120 maybe is too high. So I will say, in this case, I think if I set the threshold at 115, what means for all the pixels with the intensity higher or equal to 115, I will consider it as cell. It's showing up red here. Everything below 115, that's the background. I don't care. So I decide 115 is the right one. You may ask like why the 115 is good. If you choose 110, why that is wrong? So 110 is not wrong. It's your choice. It's your data. It's your choice. It's your right to choose what this value is. You choose what you think is the best represents your data. Here, I will say this is my data. I say 115 is good. So once I set 115, make sure this one dark background is checked. So now I'm going to apply it. Before we haven't applied, we keep kind of changing it. It's like when you're doing the image, you do a live scan. You just live preview just to check out the parameters. Once I think 115 is good here, I'm going to actually apply it. I will click the apply button. What it means is when you apply it, it will make this image what we call the mask image or binary image. Let's say I click it. You will see this image become a black and white image. We call it the binary because we only have two choices for the mask image. If you move the mouse to the white region, you will see here about the value are all 255. That's the highest intensity value for the 8-bit image. If you go to the background, this will be 0, getting? So that's what we call the binary image. It only has 2 intensity values. So why we do this is now we make this image very easy for the computer, for the program to identify which pixel we actually want it to calculate. All the pixels, if that's 0 is black, we don't care. That's the background. We don't want the program to pick it up. We only want to pick up all the pixel which is white, which we consider belongs to the cell, which is our signal. So once you get a mask image. I would say this is kind of a very good mask image. Once you use the thresholding to get a good mask image, I would say everything else will be manageable. You still need to do something on it to get what you want, but once you get a nice mask image, which you can clearly separate the pixel of what you want to the background, then you basically finish your analysis part. So now what we'll say is we want the software to work on this image, not here. Here is very hard to work. Every pixel has a different value. Getting? We don't know which one belongs to the cell, which one belongs to background. But here is just much better to work.
Excuse me, Lai?
Yeah.
You have a question?
Sure. You can unmute yourself and ask.
Oh, I was just asking in the chat. I was asking if in the threshold menu, there's the OTSU.
We will go through that later.
Okay.
That is the algorithm that helps you to decide. Get it?
I see. Okay. Mine started as default. Should I change it to OTSU?
That depends on. We're actually just right about to go through there. Yeah.
Okay.
Yeah. So this is a good. Also, this is a good mask image, but again, if I close this one, so it's your choice. It's your. You may think maybe this one, 112, will be a good. Maybe this 135 is good. It's always your choice. Yeah, getting? There's no way to tell what is the best or the right choice. It is your choice. Yeah, getting? You have to make the decision. Getting? But once you make this decision, you have to use the same value on all of your images, so you can compare the results. So all the image acquisition and digital image analysis, I will say the emphasis is not on how good you can get the result, get a perfect result from a single image. It's always how consistent your analysis is. You use the same protocol, same treatment on all the images. All the images are taken under the same condition, and you analyze them through the same way. And then when you get a result, you can compare them between each other. It's always the comparison, the consistency, which matters. So here you can say 135, 120. The value you choose decide everything on the result. You change this from 120 to 135, all the results, the size, the total intensity, the mean intensity will change. But that doesn't really matter that much. Getting? You want this one to be a reasonable one. Getting? But the more important is you want to use the same value. When I go to the next image, I can still use 120 to get a reasonable outline for that. And then this is why here is all the choices come from. So this is, if you go through here, I can say you have a default. Once you click default, it tells you the changes to 123. If I use this one to Huang, let's change to 108. You go to the, like this is OTSU. That's the same as the default. And like the triangle, it goes down. So those is what we call the algorithm. Getting? Those are published algorithm. What the ImageJ uses is a very commonly used algorithm. I think those algorithms is basically they have a specific way to calculate what the thresholding should be by their assumptions. Getting onto that. If you go through the ImageJ, the NIH, the website, you can actually find all those the original the papers, how they do the calculation. So what it does is they read all the pixel intensity, they get the histogram, then they have a way to calculate what they think is the best thresholding value. Getting? Actually, in the folder, you can actually see one, it's called the thresholding survey. if you open this paper, that's actually quite old paper. They actually compare the different algorithm, how they calculate this one. I think this is like any math papers. When you look at those things, you don't want to read it. No one want to read it. I don't read it. I think I read it maybe 15 years ago, but I never want to reread it again. The good thing is that we don't need to understand it. We only need the smart people to figure it out. They found a way to do it. My job is to say it works for me or not. Ready? If you're interested, you can go through it. Ready? But I don't say it will be any help. Ready? My goal is like I look at my image. I go through all those ones. I think if I use the percentile, this threshold is 88 is 2, no. Interval, that's maybe okay. Lee, maybe okay. Actually, Lee is actually exactly what I choose. So I will use this one. I will think this one is good. So what they did is they read all your pixel intensity. They make the decision for you. Ready? You can still freely choose what you want. Ready? But you can also ask the program to do it for you. So why the program has advantage, yeah, getting? And actually in the next week when we have more special topic to concentrate on the thresholding and the segmentation, we'll talk about that is the thresholding method can overcome some just background change on it. So I would say, as I said, I want you to use the same thresholding for all images. Getting? You should, but that depending on all your images are taken under the same condition. They have the similar intensity level. They have the similar background intensity level on that. But those is kind of easy to say, but hard to achieve. If I have an experiment last for 4 months, 5 months, you take the picture, even you're at the same microscope, you're using exactly the same condition, you reuse all the settings. But during this time, the microscope may change, that you may change to new laser, getting? You may change to new detector, getting? All this sensitivity change, and also you cannot really control your control sample and experiment condition through the staining process. They have the same background level. So that's it. If you have got under one condition, somehow the background is just high, getting? Then this algorithm can actually compensate that pretty good. I will say you. So let's say if this image, when I use the Lee, it gives me 115. So now let's say I have a different image, but somehow in this case, the background just becomes high. I will say I just add 30 into all the pixels. Now if I still use the 115, you will say it's kind of a no now because the intensity goes up. We actually have a very high background in this case. Getting? So 115 won't work. It worked for the previous image. It doesn't work for this one. But if you say, I actually use the D, getting? You will say now it goes to 146. It basically raises about to 30, almost the same as I raised the mathematically, just artificially raise the background. So it can compensate on those the background change thing. So even on the different, you have an image taken because the background is high, it can still compensate that, give you a reasonably good outline for the cells. You can still identify the cells better, getting, even though this change. So I would say, because you use the same algorithm for 2 images, even it gives you the different thresholding value, you can still say that I do that, I treat them the same. I let them go through the same algorithm, the protocol to calculate this threshold. So you can choose. The best way is that if all your image you can fix on one thresholding, that will be the best. But by my experience is that in majority of on the real life getting, this doesn't work. The images change. You have the control image, you have the experimental type, you add more things into that. You cannot really control all the background that's the same level. So in this case, if you use those algorithms, that can actually compensate this quite good. So you can try which one works the best, getting. I normally use like a default Huang, Li, OTSU, triangle, those things. It gives you different number. What you do is you try to find which one works you the best, works on majority of your images. Then you can fix it. You have to use the same one on all your images. So let's say for this one, let's go back to the image and let's say I did this one. I use the threshold holding. I would say I use the lead. 115. I apply it. So this is a mask. So why this one will help us to identify the cells. Before when looking at the cells, I draw them one by one. But now I think it's much easier. I can just let the program to say, okay, I want the white object. The white one is the object. Just give me the outline of each white object. That should be simple. That should be what exactly the computer is supposed to do. So I will ask the ImageJ in this case, give me the outline, which is one ROI for each white object in this mask image. So this, I will use the function is analyze particles. That's basically, I would say, probably one of the most used functions you will do, especially if you're doing for the cells. Analyze particles. So this is the window. So I will just make it the original one would be size. That's a 0 to infinity. The circularity 0 to 1. We want to include everything. So basically what it tells is that give me everything, any size, any shape, a white object inside this image. By the end, apply the ROI to the ROI manager. So now I will click OK. Now I can say to draw all those ROIs, and then we can apply this one to those selection. So you can look at them more closely. So I will say, I will take it. I think it's reasonably good. But again, your sample, your image, your data, your choice. If you think this is a little bit too small, we should also include more on this one. You can change the threshold into a lower one. And then it will go more out into there. What I will say here is very good. It draws total of 60 cells in just a fraction of a second. Yeah, getting? So I would say it did a very good job. And then I will say, now I want to measure it, right? So this is ROI. I'm going to save this. So this is, this will be the, so this is ROI. And we're going to set the measurement, size, mean intensity, total intensity. I measure. That's all the 59 cells. I save it as the XLS file. So as long as you have a good nice mask image you get, you can use the analyze particles. So very quickly to give you all the white object into that. And then let's say this is my mask image. To be safe, I will just save it as a TIFF. And name it mask. Getting. Once I get the mask, I will try to do something else on it. So this is a mask. And now let's say I go through the analyze particles again. Okay. So let's look at this the image. So this is all the cells we selected. So you feel like there's a couple of things we need to be careful on this. This looks good, but I would say there's one thing here is like this one. This one, number 7. I think this is too small to be a cell. This is probably just some kind of cell debris. Yeah, getting? It's not a real cell. My cell should have a reasonable size. If it's too small, somehow it has the debris has like especially for the DAPI signal, they have a very high intensity, but it's too small. So I would say when I'm looking at this one, I want to set up a size limit. Anything is too small, I don't count it as one cell. So now I can close this one. Let's just do it. So here is what your size limit is. It gives you a thresholding to filter in the size. So I will say the size has to be at least, this is all pixels, and needs to be 100 pixels. I do it. So now I will say it doesn't count this one. It doesn't count this. It doesn't count this. So you can set up a size limit, getting? Based on your understanding of your data, you know your data the best. You know what is the smallest size should be. I should exclude it. So now when I'm looking at here, I do not include this one. I do not include this one as a cell. You can also put a higher limit on it. You can also put it has to be smaller than maybe 2000 pixels. Let's actually include everything. Let's try maybe 1000. 1000 is so let's say maybe just 500. So now it gives you the cells only between 100 pixels to 500 pixels. All the bigger ones, it doesn't count. So it just gives you a filtering case that you can use to identify what is the best you want. So I will make this one still the infinity. I will say this one. I would say this looks kind of pretty good. Okay? I identify the cells and they are, I don't count all the smaller ones, which they are the dead ones. Okay? Getting? But you may still find there are some other problems in this case. So now if I began to measure it, I measure the size, okay? Then you will be able to say that when I measure the size, you're also measuring size for this one, this one, and this one. But they are not the whole cells. They are only part of the cell. They cut off by their either by the CCD chip the edge or by the scattering patterns you design. Getting? So when I compare the cell size, I say this is a control condition to a treatment condition, this cells doesn't count because the cell size is not a real size. It's just a partial of the size. So when I count the cells, when I identify the cells in here, I don't want to count anything on the edge. Getting? I only want to count the whole object. The whole object is inside the field of view. So we can also do that. I can just close it. So if you do this by analyze particles, you can very clearly, I will close it. If you manually draw 50 ROIs, always save it first. Once you close it, you have to redraw them. Okay? But here, I know we can always very easily to get it. As long as you have the mask file, I go to analyze particles. I want to go about 100 pixels. And then I want to add to the ROIs. And I want here. I want to exclude on edges. Okay? So every white object on the edge, it will not count. Now I click OK. So it doesn't count this. Now those on edges, it doesn't count. It also doesn't count those two because they are too small. No. So now those are the cells. We have a total of 40 cells. Getting? 你昨天 they are full whole cells within the field of view. Getting? And we actually get it pretty quick. Getting? You manually draw it, I would say at least take 10 to 15 minutes. Getting? But now we just go through a image, adjust thresholding, play around just to get what we think the best. I apply it, then we go to the analyze particles. Then we get there. So now I can save this one. I will overwrite this. And I will do the measurement. And let's clear the result first, and then I measure it again. So those are the, we have a total of 40, and I'm going to save it as the result. Especially for the, if you're counting the cells, and if you have a pretty nice kind of the contrast between your signal and the background, you can use a simple thresholding to separate them. And this will be the way how you do the cell either counting or all the measurement on that. And more than that is, once you get a mask file, you have actually a group of new functions you can use to work on those images. It will be in the process binaries. So for scope of this introduction in the seminar, we won't cover that. But once you get a binary file, a mask file, you have quite a new functions or tools you can use to work on with your image, which give you a much more powerful range to analyze your data. For instance, like here, this cell. It counts as one cell because here is one white object. But it's kind of pretty clear to me it's actually two cells. It's just getting very close. So the gap between them has an intensity higher than 115. Since it's everything higher than 115, we count it as white. Get it? So we count this one as a single object. Maybe this one is also actually two cells. So you cannot do anything on here, but once you get a mask image, we can do something what we call, if you go to process, binary, watershed, it will cut it for you. What they consider is actually two cells. It's actually two objects getting connected. So I can do a watershed, and then I do the same thing, analyze particles, needs to be 100 pixels, exclude everything on the edge. And then we go back to the, so this is, say, this is the original, this is you added. The watershed, sometimes it works pretty good. Sometimes it doesn't work that good. They may cut something you think is actually one cell, it cut into half. So you just need to say, you need to do it or not. If it works most fine with you, you can do it. Or if it doesn't give you too much trouble, I would say I don't do those things. It's always you need to find a protocol which is the best for your image. Like now I will say, I think I get a quite good result. I get the mask image. I remove all the object on the edge, so we only count the whole object. We have the size limit, so we don't count a very small one, maybe just the debris or just some dust. And then we separate all the attaching the cells, okay? Then you can actually begin to write down this, what I call the protocol. So your goal is that next time, every single cell come here, you do the same thing. Every single cell I come here, what I will do is thresholding, either use Lee or use 115. So remember, for the first image, for the first few images, when you begin to play around to say what is the best protocol for it, you have all the freedom to change it. What is the best for you? Getting? But now once the protocol is set, you're going to analyze the images. Everything is fixed now. All the images comes in, I always go to Lee. Doesn't matter what number it gives me, I go to the Lee, I click apply, and then I go to the analyze particles. I always choose 100 to infinity, exclude the edge, or maybe I just first do a, I will first do a watershed. And then I go to analyze particles. I keep the same setting. I click OK. Then I will accept all those ROIs, or the cell ROIs. Total of 44. All the images, I go through the same protocol. Which algorithm you choose, which number you choose, do you do watershed or not? What kind of size limit you use to exclude the smaller, the white object, that's your choice. You can play around on multiple of your images. You should play around with multiple of your images to get the protocol. But once it's set, you have to follow the exactly same protocol to analyze all your images. And then you can compare those results. Okay? So it's always the consistent. We treat all the image. When we analyze our images, the most likely you want to compare with different two conditions. To make sure you can actually compare them, you have to make sure they are treated the same. Then the difference showing up is actually coming from the sample itself. It's not by some other different choice when you use to analyze the image. It's always the consistent. Is much more important than you get kind of ideal perfect result on a single image. For every single image, you can always play it long enough to get what the best result you can get. But that's not the point. Our point is to find the protocol which you can apply to all the images. And then you use the same protocol on those images, then I get the result. Then the results are comparable. Like for the image size, it's clearly on here, let's say close this. You have a higher threshold holding value, your cell size will be smaller. You have a lower thresholding value, your imaging size will be bigger. That's always not like that. So if you want to compare the cell size of the control and the treatment, you have to make sure the thresholding value you use are the same. Or at least you have to use the same algorithm. If you can't, they have a different background thing. Just always try to take the image. When you acquire the image, take it under the exactly same condition. And when you analyze the image, analyze them under the same protocol, the same condition. It's always the consistent. is much more important than what a perfect value on a single image is. And you can use to say different. I have kind of the folder called practice. Those are the different images. Getting you can try to work like this for the Android. Getting where you, if you want to identify the Android size. Getting, but this is RGB. The image sometimes to thresholding the color image is always kind of difficult. It's kind of very tricky. So I normally just do is I force it into 8-bit image, a black and white image. And now actually the background is more like a high intensity. I don't like that. So I actually invert it. So now I'm working on the white object. So I can do the threshold holding. Then I can play around to say, okay, I get it. Something like this. Then I apply it. So I would say this is why the original image. Let's look at here. Like this. Those are the 3 embryos. This is also the 3. So I would say I want to identify them. Now let's see if I do the watershed to cut them to go through process binary. Watershed. You will see it also cut it something like this. The reason is if I do undo, you actually have some holes inside it. Once you have a holes inside it, it will try to threshold the you try to watershed it to cut it. So now we can actually, once you get a mask image, I can go through the process binary. There's actually a few holes. It can fill the holes for you, and now you do the binary watershed. It will cut it like that. And I will say for this one, I will analyze particles. I'll say, I'm not sure what, probably this is 25 will be good. I also include the edge, add to the ROI manager. This is all the some of them are good. Some of them probably they should be 1, but actually it's also cut. Getting? So that will be, you can play around this more. I'll say this one I will change here. I will say maybe even more, 75. I would say it's good enough. Getting? I will identify those how many embryo inside. I want to calculate their size. Getting? But one thing you can say is it also gives you this. Those are scale bar, which is not what we want. But the scale bar is actually showing up here. Let's say this should be the overlay. It's actually a big size. Getting? I cannot really use the size to discriminate it. Getting? So that's something else we can try. If you play around those one more, you can also say this is the circularity on the shape. I will say my embryo, the sample, has to be kind of round. Getting? Cannot be like a single line here. So I will put that as a 0.5. So the circularity at 0 is a straight line. If it's 1, it's just a perfect circle. Getting? So I would say it should be something around 0.5 to 1. Then I will have everything else, but I do not have this shape. So now if I apply to it, then I don't have, I still have this part. Maybe I can use more sides to remove this one. I will say maybe 200 is good. Yeah, I think it's fine. So I have the enough get all the kind of the embryos here, and I don't count this one. This probably is should be 1, but it cut it. I will just take it. I think for all those 30 cell, the embryos, we have 1 may have some problem. We may count 1 more in one image. We may count 1 less in another image. I will just take it. I'm not a very high standard guy. I think that's what I care is about not the perfect method for this image, but this protocol can actually apply to majority of my image like this. Like every time I pick up this image, what I do is I make them the 8-bit image, grayscale. I invert it, so the background is kind of null. Then I use some thresholding method. I apply it. I fill the hole. I watershed, and then I go to analyze particles. The smaller size is 200. The circularity is 0.5 to 1. I exclude everything on the edge, and I add to the other one. So here I may have cut 1 cell into 2. I will just take it. Okay, I think it's good enough among the 30 cells. It actually should be probably 29 by humanly check. Getting this gives me 30. I will take it. If you don't like it, you can kind of optimize your the protocol. You may later on to end up, they get all the here are the same. Here you also do not cut it. Okay? But you need to make sure your protocol can work with other images too. Okay? So always the goal is not to make a perfect analyze on a single image, but to make sure your protocol is reasonable enough you can apply to all your images. Okay? That's always the most important thing. Okay? At the beginning, I will say many people, they just get into a trap, like I take so much time, I want to analyze the data to exactly like what I will purely manually do it. Once you ask the program to do it automatically, you have to make a choice. It cannot be as good as you manually do them on a single image. Get it? You have to do it. You have to accept a kind of a standard. We have to treat them the same, and results are reasonably good that we can accept into this. I mean, what kind of standard you have is your choice. But just to make sure, your goal is to make a protocol. You will stick with this protocol, apply to all the images. Getting? And the good thing is not the result is more reliable, consistent. Once you have a protocol precisely set, you can convert this protocol into a code. Then you can do that in a batch. Because like for us, the previous one, all the things are fixed, right? I open an image, I use the Lee algorithm to set the thresholding, I apply it, then I go to the process binary, I do the watersheding to separate contacting cells. Then I go to the analyze particles, I use 100 to infinity, and I do not include everything on the edge. Then I get the ROI, then I save this ROI. Then I set the measurement to be size, mean intensity, total intensity, apply to the raw image, I do the measurement, I save the result. There's no human interaction involved here. So you can put them into a batch process code. You can, so all the files come in, I do this. You can apply this automatically to 100 images in a folder 1 by 1. They will do it very quick. Okay? But the important thing is you need to have a protocol. Getting onto that. So we're about to the time. Any questions? Getting?
I have one, Lai. I was trying to follow along with you, and I think I just missed something fundamental. So when you drop an image into Fiji and you make the binary image, whenever I do my thresholding, I lose the original image, and you were showing the thresholding, the black and white along.
I open the raw one again.
How did you get it so the
you can do
the selected
this
ones show up on
Okay.
the original image?
So if I do this, you just make sure this is the active one. This is active one, and you can unclick show and then click show again.
Okay, thank you.
This can apply to all the images. You just make sure this is the active one. You can unclick show, then click show again.
Perfect. Thank you.
Hi, this is Asha. Thank you.
Hi.
I missed the part on where you show multiple different results output. So you have your ROI manager with one lane, and how do you get more information into your results?
You can press T, and you can basically, if you add more, you can like add. Is that what you're interested?
No, when you saved the results, you also not only had the intensity, but you had multiple different measurements.
Okay, this is the set measurement. You can choose. Is that your question?
Yes, I think that's my question.
Yeah,
so
so
that's
you can
analyze,
choose analyze set measurement.
Ah, perfect.
So
Thank
those
you.
are all the basic measurement you can get from the ImageJ. Everything beyond that, you have to find a way to do it by yourself, either by combine some of this, or you have to write a code that the ImageJ, the macro code, you do it yourself. So the last few minutes, I will just kind of a demo. If I working on a real cell, getting? So let's say if I can real cell image. So this is a fluorescence image. I want to count how many cells, the same thing, gets automatically gets the ROI of all the cells and try to measure this. So the same thing, threshold holding it. So you can choose which one is the best. I will say, I will go through something. I think the D is good enough. I will apply it. And there are some holes inside it that give us the trouble when we do the watershed shading. Because now if I directly do the watershed, you begin to cut that into pieces. So I always do a binary, fill the holes. And then I go to the binary watershed. Then I go to analyze particles. In this case, you will say, now here, the size is not pixel, it's a micron square. Because here we actually has the right pixel scale. We know each pixel is how many micron. So you can, when you analyze particles, when you use here like a 10, this 10 is micron square. Just remember. So now you will say maybe I want 50. I click OK. I change this to 0. You don't have anything selected because now none of them is bigger than 15 micron square. Normally I will say I want to use a pixel unit. I will say I will count all the objects which are at least 50 pixels. Now we have this like that. So this will depend on, so many times I think for me, when I look at this image, a digital image with composed of pixels, I always feel it's much easier for me to guess what's the image size in a pixel unit. So I always try to do this. I check the pixel unit. So everything here 50 is 50 pixels. But you can also, if you have a more kind of a clear idea in your case, you think the micron square is better for you to understand is fine. But just intuitively, when you look at the image, it's all in pixels. That the pixel unit is a more natural way to do it. Okay? And then I will say, let's here go. This is our selection. I would say it's actually, I would say it's pretty good. Really. Someone may think that this may not be a cell, it may be a dead one, but you can use the size to exclude this. And those may be actually 2 cells for this one, actually 2 cells, but now it only counts as 1 cell. Okay? So again, for me, I would say I'm not really a high standard guy getting. All I feel is that if I look at the image, I think this, a clear, simple protocol give me a reasonable result, I will accept it. So again, it's always keep in mind, it's always your choice, but always just keep in mind, our goal is to not to find the image process give us the best result in a single image. If you want to do that, I would suggest you manually draw those ROIs. That's what you think by your personal preference, what is the best for this image. Okay? Our goal is to use the same protocol, same treatment to apply to all the images. Then we can compare the difference between different conditions. Okay? So it's always try to go on multiple images, play around, and then find one protocol I think that give us reasonable results on majority, most of the images. Then I fix with this protocol, then go through all my images. Okay. So any questions? Yeah. Yeah. So this is about for today. We're about to end. So for next Monday, the beginner 3 we're talking about here. All the images we get is actually the pretty good one. Once I get the image, I can directly use the thresholding to achieve a nice mask image. But in reality, probably your image, you cannot directly go through this one to get that. You need to do some pre-processing on it, do some filtering, do some background subtracting on that one. Then you can get a mask image. I will introduce more tools on the ImageJ, how to treat the sample on those. Getting? So I guess I will see most of you on next Monday. So for today, we will end here. Thank you very much to join
Thank
the
you.
seminar. Getting? Okay, so bye.
Thank you.